Okay, team, welcome back. Let's talk about the discussion for week 4 that's about worksheet 4C2, where we have this notion of an objective function. There's a video by Sister Joanne that you should go through, but I want to sort of add to that. Sister Joanne goes through number 1. I want to work on number 2, and let's talk about what it means to be an objective function and then some constraints. This is a topic known as linear programming, and I don't want to get overly confused with it, but what it's doing is it's finding a solution to inequalities, to a system of linear inequalities. And that's why it's presented in this chapter. But what it really represents is an optimization problem. What's odd about these problems that we've given you in this week is that there's no word problem associated with it. Usually this is wrapped around a word problem, like trying to optimize something where you have two variables, but you have these constraints that you have to stay within. So I'm not going to try to concoct an example, but I will show you how it gets done. So let's look at number 2. We have an objective function, 3x plus 2y, that we want to maximize. We want to optimize that. We want to make this as large as possible. But we've got constraints. First, it has to be positive because these things probably represent real world values, and it doesn't make sense to have negative of something. For example, if you're trying to optimize the purchase of two different types of things at different prices, one of them, the X thing is at $3 and the Y thing is at $2, obviously everything's going to be positive. So we have constraints. They has to be out in quadrant 1. So it's X is positive and Y is positive, or 0. X plus Y, so the sum of the two have to be less than or equal to 40. The sum of X plus 3Y has to be less than or equal to 80. And the sum of X plus 5Y has to be less than 130. So what we do is we use Desmos. I showed you that on our Zoom call, and I'm going to show you that again. We go into Desmos, and we just graph each one of these. And you can see this is X plus, the red is X plus Y is less than or equal to 40. This color is the X plus 3Y is less than or equal to 80. And then X plus 5Y is less than or equal to 130. So what we're looking for is the intersection between these 3 points that is in the positive quadrant 1. So X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. I could add those as constraints up here too, but I'm not gonna. And what we're going to do is then say, what is the intersection? What is the region that is shaded by all the colors, all 3 of these, that satisfies each of these inequalities? Well, it's bounded by, and again, it has to be up here in quadrant 1. It's bounded by this, 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 and this. Well, so now we have to say, all right, we have 4 possible values that could represent the maximum. So we want to plug these values back into the function, the objective function, and see which one is the highest. So we have 0.26, and I'm going to use a tool known as Wolfram Alpha to do that. So 0.26, we're going to evaluate 3x plus 2y at 0.26. That equals 52. Now, let's look at 5.25. 5.25, and that equals 65. Okay? So that's a little bit bigger. Now let's look at 20.20. 20 is a point that also satisfies it. And that equals 100. And last but not least, we look at 40 and 0. And that equals 120. So our maximum objective function is at the point 40, 0, where it equals 120. So this point right here is the point that represents the maximum of our objective function. If we plug in 40 and 0, we get the highest number. I hope this was helpful. Try to do the same thing using Desmos for the third problem, and you should be well on your way. Take care.